I like this example of how to calculate torque. Okay? This picture is a pretty straightforward picture if we sort of redraw it to include just the rigid body. Now, the rigid bodies now, when we do rigid bodies, they're not point masses. So there's actually a length to these things. So I'm going to represent this wrench by this particular length that I have drawn there, and I've applied a force in this direction. Okay, kind of like that. So again, these are notes that are not on your equation, on your notes packet there. When I apply a force on it, I have to understand where the axis of rotation is. So right here, I'm going to call this the axis of rotation. Yes. Yeah, what I do with all of these, remember, is this gets saved as a video, so you can watch the rest of this. Yeah, so you can go. Okay? So that there is the axis of rotation. Now, here is this force F. And it doesn't matter how we draw it out. And again, as a force diagram, these actually have to be drawn out. Okay? Now, what I want to make sure you understand is this thing called the line of action. The line of action is an imaginary line that goes along the length of the force in the direction it's coming from and in the direction it's pointing it. So that's the line of action. Okay, so I'm just redrawing what you see in the picture there. Okay, what's really important is this thing called the moment arm or the lever arm. So you'll need to just remember, I think I call it the lever arm. In Physics B, we called it the lever arm, right? Okay. The lever arm is the distance from the axis of rotation to the line of force that makes a 90-degree angle. Okay? Does that mean that it's got to also be the shortest distance to that?
Yes.
Okay. Good. Okay. Okay. So this is what we call the lever arm. All right? It's the distance from the axis of rotation to my line of force that makes a right angle. And you said, yes, it's got to be the shortest distance? Okay. And it's the shortest it would be the shortest distance from my axis of rotation to my line of action. So for the time being, we're going to look at torque simply as this force times this lever arm. It's tau in torque. That symbol is tau, lowercase t in Greek. Okay? Greek lowercase t. So tau is equal to the force that's applied times this lever arm. All right? Okay. So, I meant for us to do all that work on this page, but we did it already. So if we look at this problem is going to be in equilibrium. So we're going to have a total of 3 torques here. Okay? Now, so there are some conventions when it comes to torque. So clockwise would be this way. For some reason, clockwise is negative. Okay, so that's the symbol that I use. And counterclockwise is positive. On the AP test, if you write this down, what you're doing is you're telling the AP grader that that's the convention you're using. Okay, actually you only have to draw one of those. Okay? All right. So it says, what must F be to achieve equilibrium? So what I like to do is I like to take all of the counterclockwise ones. And equilibrium is like this. Equilibrium is when the sum of the torques, okay, if we add up all the torques and they equal what? They equal 0. Okay? So if the axis of rotation is in the center, first of all, how many forces are there on here? How many forces are on this setup here? There's 3. Okay, two weights that are producing two different forces, and this force that's pulling to the right. So if there are three forces, for this particular problem, how many torques should we calculate? Yeah, we're going to look at 3 torques. Okay? How many of those torques are clockwise and therefore negative? Is F negative? Yeah, well, the torque will be negative for it, right? Okay, what about the 2 kilogram one?
Why would that one be negative?
Okay, because it's pulling in such a way that it would turn this in a clockwise direction. Okay? All right, so one of our torques, one of our negative torques is, I'm just going to label that like this. So our unknown torque for F, I'm going to label as the torque of my unknown, just question mark, is going to equal the force, okay, of my unknown, times the lever arm, which I actually know that, right? The unknown lever arm is 3 centimeters, right? Okay. What's my other torque? That's unknown. It's the one with the 2 kilogram one, right? I'm going to label that T sub 2. Okay. That's going to equal the force. What force is it experiencing? What force is the 2 kilogram object? Downward. Okay, so it's 2 kilograms. 2 kilograms times what? To produce the force. Yeah, it's got to be 9.8. Right? I'm going to leave the negative signs out for the time being, just so we can put the negative signs in later. So this represents the force, that's F sub 2, okay, times its lever arm, okay, which we'll call, let's actually put the value in. What's its lever arm? Okay. If the 2 kilogram one is on the 3, right? So 0.03. 0.03 meters. So that's the lever arm. This represents the lever arm of 2. Okay? So those are my 2 negative torques. Okay? Let's look at the positive torques. Okay? The positive torque would be from that one. So I'm going to call that torque sub 10. Okay? So its force that it's experiencing is what? What is its force? Yeah, so 10 kilograms. I heard someone say 98. So 10 kilograms times 9.8. Okay, meters per second squared. And what's its lever arm? Okay, 0.02. Okay, so its force is F sub 10, and its lever arm, I'm going to call L sub 10. Okay? All right. So now I've got to add up all these torques and make them equal 0. So you know what? Let me save some space here. Okay, so I'm going to take, let's start with my positive torque here. So 10 times 9.8 is going to be 98 newtons, okay, times 0.02 meters. Okay, so I'm adding them up. These are going to be negative, so I'm actually going to subtract them. So minus, okay, Newton meters. We'll talk about that in a second, okay? And then we're going to subtract this torque that's negative. That's my unknown, F sub unknown. What's the lever arm on my L sub unknown? What's this lever arm for that force right there? Yeah, it's also going to be 0.03. 0.03 meters. Okay, and I'm also, with that, also going to subtract, I'm running like this because I'm running out of space. My other torque, which is 2 times 9.8, what is that, 19.6? So 19.6 newtons times this lever arm of 0.03. All right, and that equals 0. Okay, so this equation here that I'm circling, that is a representation of that fact there. The torques are equal 0. Okay, so I've got one equation with one unknown, so can this be solved? F sub unknown? Yeah, did someone already calculate it? I did this. I got 45 point. Okay, good. Let's go 45.7 newtons. Okay. All right. So that's just a practice problem. So the torque problems, I just have a handful of them. Yeah. Oh no, the negatives only count for the torques. Okay. So that force, yeah, the force actually points to the right. Okay, but the torque is determined to be negative when it's clockwise and positive when it's counterclockwise. All right. Okay, so that kind of ends that. So, right, because I think we might be filling out part of that. So I think the conditions for equilibrium. Yeah, it's on the top left-hand side. So the equilibrium definition, it starts on the bottom of page 2 of your notes packet, then goes to the top of page 3. Okay? So the example we will look at, and we will apply this to, is the example there. Okay, where we've got essentially this, we've got this person, this firefighter on this ladder, okay? It says the firefighter's weight is 875 newtons, the ladder's weight is 355 newtons. The wall has a normal force, but no friction. The ground has both normal force and frictional forces, okay? And the question at the bottom says, what is the normal force applied by the wall, and what are the normal frictional forces applied by the ground? Okay, so let's go to the next page here. Okay, so here are the conditions for equilibrium. Okay, so there's 2 conditions. For static equilibrium, since we're dealing with 2 types of motion, both rotating and linear, static equilibrium is when there's nothing moving at all. All right, so it's neither moving in a linear fashion, nor is it spinning or rotating. Okay, so that's static equilibrium. So just about all of the study of civil engineering is based off static equilibrium, because generally speaking, you don't want your buildings moving, right? Okay, so the sum of the forces equals 0. Actually, that's changed, obviously, in the last few decades with what we learned from the Loma Prieta earthquake, and even before that. Now buildings are being made so that they actually do move and absorb some of the shock when there's an earthquake. Okay, dynamic equilibrium occurs when the system is moving with constant velocity, so in its linear motion is constant, and both its rotational motion is constant as well. Okay, so if it's translating means moving just in a straight line, okay, with constant velocity, or spinning with constant velocity, right, or rotating with constant velocity. Okay, all right. So the conditions for equilibrium are simply that: the sum of the torques equals 0, and the sum of the forces equals 0. All right. So we're going to make sure we understand that we look at both the sum of the forces and the y. Okay, the sum of the forces in the y have got to equal 0, and also the sum of the forces in the x have got to equal 0. That's sort of implied in that equation. Okay, so those are our conditions. Okay, so as far as your notes go, they say, what does it say? You mind if I borrow that?
Sure.
So equilibrium definition. Okay, so there are definitions. Okay, and then on top of the next page, the conditions. Okay, so this condition, the sum of the torques equals 0, and the sum of the forces equals 0.
Should we write down static and dynamic equilibrium?
I think that's on the previous page for the conditions. Yeah. On the bottom left, bottom right.
So right here?
Yeah.
Okay.
So just as notes, maybe you just want to write down static equilibrium, no motion at all. Okay. And then for dynamic equilibrium, rotating with constant angular speed or moving with constant linear velocity. Okay? All right. So that takes us to our example. All right. So actually, a couple years ago, there was an example really similar to this on the AP Physics C test. All right. So what we have to do is we're going to follow those steps. So those steps that I had you guys copy down, we're going to follow those steps. The first thing is to draw a force diagram. Okay. Now, in our force diagrams, we've got a rigid body. So the rigid body has to be drawn as exactly that. And for us, for the most part, our rigid bodies will be just a line. Okay? So draw that line out that represents the ladder, because the ladder is the rigid body in this example. All right. So the force diagram, we need to draw our forces. So what forces are on that ladder? Okay, the firefighter's weight. Okay, so I'm going to label that. I'm going to have, just because of my notes, I'm going to use certain symbols here. So I'm going to use W sub F here for the firefighter's weight.
Is that where our origin for torque is going to be?
No, we're going to make the
At the bottom of the ladder?
yeah, we're going to make the axis rotation the bottom. Okay, and then in the middle, okay, what will we have in the middle of that? We talked about how we're going to put the weight at the center of mass. We haven't talked about that. Okay, so the weight of the rigid body, generally speaking, if it's, we're going to put that at the center of mass, right in the middle. Right. So right at the center, we will put the weight. We'll call that W sub L of the ladder. Okay. What other forces are there? Wait. Okay, the normal force, there's two normal forces. What? Okay, from the wall, they say there's only the normal force, and again, I'm going to use kind of a weird symbol here. I'm going to use P, it's just because those are the notes that I have. Okay, as that force. And what are the other forces? Okay, the force from the ground, so there's a normal force from the ground, and I'm going to label that G sub Y. Okay, that's a normal force. And what else? Okay, and I'm going to label that G sub X. Okay.
Shouldn't it, P be like, make it towards 90 degrees with the wall?
Well, no, because the wall is going to point directly to the left. Push it directly to the left. Okay? All right. So our next thing is to choose our coordinate system. And we said which way was positive? Okay, as far as rotation is concerned. To the right will be positive, and up will be positive. Okay. What did we say was going to be positive as far as rotation? Counterclockwise. Okay. So sometimes you'll actually see me use this symbol where we say that direction and that direction, and then that direction. I know that looks kind of confusing, but these are the directions that we'll call positive. Okay? Upwards positive, to the right's positive, and counterclockwise will be positive. Okay? All right. So the step 3 is to look at the forces in the x direction and set them equal to 0. So that's what I'll do at the top here. The sum of the forces in the x should equal 0. Okay, and what forces are they? What are the only forces that we have in the x? Okay, so I'm going to write that down as gx, and I'm going to subtract p because it's going to the left. I'm just going to put the signs in now. Okay. And then we're going to look at the sum of the forces also in the y. Okay, and we're going to set that equal to 0 as well. Okay, what forces are in the y? Okay, gy, what else? Okay, gy. Okay, and I'm going to put a negative sign in front of the weights because they're going downward. Okay. All right. Do I know any of these values? Are any of them explicitly given to us in the problem? Look at it again.
W2 and WF.
Okay, good. The ladder and the weight of the firefighter both given to us. So gy we could actually find. Okay. So we would put in negative 355 newtons there. Minus 875 newtons. That'll equal 0. And so gy will give me a value of...
Since it's not in the... Since none of those are in the same direction as the normal force, can't you just skip that? All those steps?
Say it again.
All it asks for is the normal force of the ladder. So you can just skip all that. Right?
No, we still need to find, we'll still need to find P as well, right?
Yeah.
Well, yeah, we might, we need this. This is one of the things that was asked for us. Yeah.
Oh, it asks for friction too.
Yeah.
Oh.
Okay. All right. So these are our equations so far, okay? So we can't go any further because the other two, Gx and P, we're going to need some other equation. All right, and so we go to step 4 that tells us that the sum of the torque should equal 0. Okay, so this is as far as we got with the sum of the forces in the x and the y. So now we want to apply the fact that the sum of the torques, the sum of these torques equals 0. Okay, and I want to make a table for this. Okay, I want to make a table, and we're going to label it with 3 things. We're going to look at the force. That's providing the torque, the lever arm, and actually calculate out the torque. Okay, so the first force I want to look at is the weight of the ladder. Okay, so the weight of the ladder. How would am I actually given that value? Okay, so that's given to me, so I know that that's 355 newtons. Okay, and let's also look at the weight of the firefighter. Is that given to me? Good. That's also given to me as 875 newtons. Okay. P I'm looking for, so I'm just going to label that as a generic P right there. Okay. Now I want to calculate out the lever arms. Okay. So remember, before we calculate out the lever arms, I want to draw out the lines of force. Okay, to find these torques. So I'm actually going to use a different color here. Let me use like green or something to figure out. Okay. So let's go with the weight of the firefighter. Okay, no, I'm sorry, the weight of the ladder. Okay, and look at its lever arm. Right? So if I draw the lever arm, before I get the lever arm, I first have to find the line of force. Where do I draw the line of force? For the weight of the ladder. Okay, right there in the middle, but in what direction does it go?
Negative.
Okay, so remember, it goes along the length. It goes along the length of that force. Okay, so my line of action for WL goes just in the same direction as it points and back towards where it was pointing. Okay, so I'm going to do that for WL. I'm going to do that for the weight of the firefighter. Okay, and I'm also going to do that for P. Okay, so those are my lines of action. Okay, now I'm going to find the lever arm. Now, before we go on, let's let me just talk about the let me talk just real quickly about the axis of rotation. I kind of skipped this, which is actually kind of an important thing. I'm going to make the axis of rotation right there at the bottom left. Any idea why I decided to make that the axis of rotation? Okay. The reason for it is this. I want to solve this problem in as few steps as possible. These problems could actually be solved by putting the axis of rotation anywhere along that line. But if I put the axis of rotation at gy and gx, will gy and gx produce a torque? No. No, because remember, the lever arm will be 0 for gx and gy because they're at the axis of rotation, so they will not produce a torque. Okay? So you always want to choose the most advantageous axis of rotation because you can put it anywhere you want on the rigid body. Okay? If we put it where there are two forces already at that location, we make the torques there 0 and we don't have to calculate them. Okay? So choosing that axis of rotation on the bottom left makes the problem a lot easier for us. All right? Okay. So what I want to do now, I'm going to use a different color. Let me use blue now. I'm going to use blue to find, I'm having trouble seeing here. All right, to calculate out the lever arms. I'm going to calculate out the lever arm for WL, okay? Remember, WL, the lever arm, is from the axis of rotation to that line of force. So from here to there will be that lever arm. I'm going to label that W. Well, you know what? I don't know if I'll have enough space. So this lever arm right here, this L, I'll put it right there. That lever arm, okay, for the ladder is going to be what length? Okay, this is for the ladder. Okay, so I want to go, the entire length of it was 8 meters. So if this is 50 degrees here, okay, the distance from the middle to, the distance from this point to that point to the axis of rotation for the middle of the ladder is going to be how much? From the middle of the ladder to the axis of rotation? 4 meters. Okay? So, but I want this length right here. This length is 4 meters, but I want this length right here. Good. I want 4 meters times a cosine of 50. So that's going to give me, and I'll just give you the value, 2.57 meters. Okay. Then what I want to do is I want to find the, let me erase this so that it actually looks neater. Okay, I'm going to erase this and that. Okay. And let's go back to blue. Okay, now I want to find the lever arm for the weight of the firefighter. Okay, so again, I got to draw that from the axis of rotation, which will go from there to there. So this is my new lever arm. My lever arm, this I label it L sub F. And the phone rings, so I'm going to hit pause here. Okay, so our lever arm, okay, if you're thinking I should probably address it if you have a question.
Well, I just don't know where the 8, how did we know the ladder was 8? Because I know it.
Oh, the problem told us that the ladder is 8 meters long.
It did?
Yes.
Oh, okay.
Okay.
I just saw that it was
Yeah.
6.3. So
To the firefighter, yeah. Okay. All right. So then let's look at where the firefighter is. Okay, so we said the firefighter was 6.3 meters. Okay, so the Firefighter is 6.3 meters from there to there. So our lever arm of the Firefighter will be that length, will be this length right here. So how will I calculate that out? Okay, so 6.3 cosine 50. And that gives us a value of 4.05 meters. Okay. All right, and I'll erase that so that we can go on and look at some of this other stuff as well. Okay. And I'll erase this just to get that out of our way. Okay. Now we want to look at the value for P. Okay, actually, let me erase all this stuff up here as well. So it kind of gets out of our way. Okay. Now when we look for our value for P, okay, my lever arm there is actually going to go from this line of action down to, again, my axis of rotation. So that's my lever arm L sub P. Okay. I don't know its value, so I just have to, I'm going to have to do the same thing. I'm going to have to go, actually I do know the value of its lever arm because, I don't know the value of P, I should say, but I do know that I can find the value of its lever arm because I know that I've got 8 meters, and that length, what trig function am I going to use there to find that length? Okay, 8, oops, I already wrote that. 8 what?
8 times cosine of
Okay. So if this is 50, we got to use 50 though, right? Okay.
Are we searching? Are we looking for the one that goes left?
Yes, it's this length.
Sine 40.
It's this length right here. Yeah. It's sine 50, right? It's not sine 50? Yeah. That's the same as cosine 40. Okay?
Other way around.
And that gives me, I'm sorry. Right? The sine of 50 is the same as the cosine of 40, right? Okay. All right. Now to solve for the torques, okay? Now we need to be really specific as far as this goes. Okay, guys, if you have a question, please ask. Otherwise, it's just going to get really annoying to have to. Okay, got a question? Good? All right. So now we got to calculate out the torques. Okay? So the torques for each of these, I'm just going to take the force and multiply it times the lever arm. But remember, we need to keep track of what's positive and negative. So let's just do the magnitudes first. So 355, so this torque is going to be 355 newtons times the lever arm of 2.57. Okay. Meters. I'm going to run out of space there, so I'm going to leave the units out. And then over here, I'm going to do the same thing. 875 newtons times the lever arm of 4.05 meters. Okay, and then my unknown P times 6.31 meters. 13. Thank you. Okay. So I'm going to get right out these values. I get 913. I'll just give you the values here. 913. The units for torque is what? Newton meters. Okay. And then for this torque's 3,543 Newton meters. Okay. And then 6.13 P. 0.13 times P. Now, which of these, let's make sure we got the correct signs, okay? Which of these torques should be negative and which should be positive? Okay, those should be negative. Why? Okay, or clockwise. Okay, right. And then P is going to be positive. So now we're going to apply our equation of the sum of the torques should equal 0. All right. So I take all my torque values. my positive 16.13 times P, I'm sorry, positive 6.13 times P. I'm going to subtract my 913 Newton meters and subtract my 3,543 Newton meters. And that should equal 0. And I'll just give you the value here, so in the interest of time, our P ends up equaling a negative 727 newtons. Does it come out positive? That's interesting. Okay. Oh, okay, so we called that, okay, I got you. So you're right. It should be, well, it's going to the left, right? Didn't we call it to the left negative? Yeah, so, oh, but you say, okay, because we switched the, okay, gotcha. All right, the magnitude's right though, right? Okay, so G sub X would be what value then, according to this equation up here? Okay, so that's going to be 727. So I switched those other coordinates, that's why those positives and negatives didn't come out right, right?
Where did clockwise come from?
Okay. All right. This is, go ahead. What's your question?
I don't know why the axis of rotation is going clockwise. Because you said that's why it was negative.
Okay. So we define clockwise as being negative and counterclockwise as being positive. Okay. So
it's going clockwise in the problem?
no, it's actually not even moving. Okay. The object's in static equilibrium. But if it were to move, okay, those forces there, if it were to move about its axis of rotation,
those would be pulling it clockwise.
Exactly.
So that means P is positive.
Yes. Yeah. So, well, no. I mean, yeah, it's not positive. Yeah, there's a difference between what's the torque. So the torques are positive and negative, but the forces. Okay, let me make sure you guys understand. The torques are positive and negative based on whether they're clockwise or counterclockwise. The forces are positive and negative based on whether they're up, down, left, or right. Okay? So, with that being said, is P being negative correct?
Yeah.
Yeah. Okay. All right. All right. So, this is the type of problem, don't be surprised if you get this type of problem on your test as far as the equilibrium problems go. Okay? Next time, we're going to look at the non-equilibrium rotating problems. And those are actually not that bad. We just use the linear analogies for them. Okay? All right. So I think I've got just 3 problems for you guys to do. You basically have this beam. They give you the weight of the beam. Okay? Let me use some color here that I can erase eventually. I don't know. Let's just go with black here. Okay? So they actually give you these things. They give you the weight of the beam, and they give you, the weight of the box that's on the far end of the beam, and they actually give you the weight of the beam itself. So we set the weight of the beam right in the middle. Okay? All right. So the force diagram is probably the most important place to start. All right? So remember, this is a force diagram of a rigid body. In other words, it's a force diagram not just of a particular point. You have to find out where on the rigid body your forces go. All right? So there are a total of 5 forces. They tell you that there's a force of tension, the string up and to the left, the weight of the box straight down, the weight of the beam straight down, and the hinge provides a vertical force and a horizontal force. Okay, so there's a total of 5 forces there. So the steps that we take is first to draw the force diagram, then to determine our coordinate system. So to the right is positive, up is positive, down is negative, to the left is negative, counterclockwise is positive, and clockwise is negative. All right? Our next step is to write out is to look at our forces. First, we have to look at the horizontal forces. We set the sum of the forces equal to 0. Okay? So the only horizontal forces are HX and TX. So I kind of broke my own rule before. I combined the component diagram and the real force diagram. So they're kind of put together there. Okay? So HX minus TX is equal to 0. In the vertical, it's TY plus HY minus B minus W is equal to 0. All right? I don't think that's that big an issue, the force, writing out the horizontal and vertical forces. I think the bigger issue is identifying the force diagram and how to draw it, and then identifying the torques. Okay? So remember what we said about the axis of rotation. I purposefully choose that as my axis of rotation because it gets rid of two forces in my torque. I can choose the top right as well. That's actually possible, but in this case, I chose the bottom left. All right? So now that I've chosen the bottom left as my axis of rotation, that means that I only have to calculate 3 torques. The torque from force on the beam, the force on the weight, and the tension itself. Okay? Now, let's look at the lever arms, on how these are calculated. I want to look specifically at the lever arm first of the weight of the box. So I drew that down at the bottom left here. So I redrew the picture. Here's the weight. Okay. It's pointing downward. Remember, we had to draw a line of action. So this dotted green line is our line of force. Okay. This black line labeled capital L is our actual beam. The lowercase l is my lever arm. So I have to calculate the length of my lever arm. The length of that lever arm is big L cosine 30. So that's what goes into my lever arm equation, slot there. Okay? I have to multiply the weight times the lever arm to get the torque. So I get a negative torque because this weight will pull it in a clockwise direction. Okay? Now, I have a similar setup with the weight of my beam. The weight of my beam is right in the middle. Okay, so the only difference between the weight of the box's lever arm and the beam's lever arm is that it's at a location L over 2. So I'm going to plug in L over 2 there as opposed to L for my lever arm and multiply that times the cosine of 30 to get its lever arm. Okay, now, the hardest part of this, I think, or the place that people made the most mistakes, and to be honest with you, I struggle with this too because I couldn't visualize. I had a hard time visualizing this, and it's in the lever arm of the tension. Okay, so I redrew it over here on the far left-hand side. So here's the tension. It told us that this is 50 degrees, that area is 50 degrees, and that's 30 degrees, so this combined angle right there has to be 80 degrees. All right? If that's my length L, then my lever arm is right here. It's adjacent to this 10-degree angle. And by looking at the picture, that's not really that obvious. Okay, so I admit that that was kind of difficult to see. All right? So the lever arm for the tension is L cosine 10, and that's why I have L cosine 10 there. All right? So the 3 torques end up being these 3 torques here. That's the torque for the beam, that's the torque for the weight of the box, and that's the torque from the tension. Any questions as to how those torques were calculated? Yes?
How did you get the negatives again?
Okay, good question. The way we got the negatives is by looking at what direction they would rotate the beam. Okay, so this force here, B, if it were actually able to move this through the axis of rotation, it would move in a clockwise direction. Okay, so clockwise we'll call negative. W will do the same thing. It will move this in a clockwise direction. So that's how we get those two as being negative. The tension T we'll move it in a counterclockwise direction. So that's how we get that as being positive. Let me just emphasize that and put a positive there. Okay, yeah.
Can you explain how you got the angle again?
The angle for which one?
10-degree angle.
Okay. All right. So as far as, okay, so this L here, that's the length of the beam. Okay. There's my tension. Okay. It told us that this angle right here is 50, right? It told us that angle there is 30. So this angle below the 50, because of alternate interior angles, has to also be 30, right?
Yeah.
So if I combine this 50 and this 30, that represents that 80-degree angle there.
Okay.
Are you not seeing that? That was kind of like
that the whole thing is 80.
Okay, so
I'm seeing how that.
let me go to a different color here because I want to save this for you guys to look at online. So let me use this darkish green color here. Okay, so this angle here, that angle of 80 degrees is this angle of 80 degrees right there. Okay? What I have to do is I have to take my tension and I have to draw a line of action along it. Okay? And anywhere between where my line of action and my axis of rotation make a 90-degree angle, or where it's closest, okay, that's going to be my lever arm. So this L here, this length here is my lever arm.
Yeah.
So because I determined that would be 80 degrees and that's got to be 90, this resulting angle's got to be 10 degrees.
Okay, so you drew that the new lever arm in yourself. That's not part of the
Yes. Yeah, that's not the lever arm. The lever arm, unless the line of action is perpendicular to the rigid body, it will always be off the axis. Okay. The only way it could be the same as the only way L could be the same, that little smaller case L and uppercase L could be the same, is if it was at 90 degrees to the beam. Okay. And again, the reason why this is hard, this particular problem was kind of hard, is from looking at the picture, it was hard to visualize that picture there that I have on the left.
So why does the weight doesn't have its lever arm is 90 degrees with its line of action? Is it?
No.
You use a beam.
No. This weight, okay. The only way it can be at So no, it's not. Is that what you're asking?
Yeah,
the weight?
Don't you always want it to be 90 degrees?
It'd be perfect if it was 90 degrees, but the weights aren't always 90. So let me give you an example here. Let me pause. Okay, so then what we do is we have to say that the sum of all the torques have to equal 0. So I take these 3 torques, okay, the 3 torques that are right here, and I have to add them up and set them equal to 0 like I did there. Okay. Fortunately for us, all the L's canceled. Right? I have a sense that maybe some people were trying this problem, got a little frustrated and realizing that L wasn't given, so they couldn't calculate it. All right. I have to admit, I looked at the problem too and thought, you know what, the L's not given, so this is going to be kind of weird. So I kind of just went with it and realized, it's possible that L might be canceled, might get canceled. So that indeed happens. Okay, the L gets canceled. Okay, and then we solve for the tension, and that's the first thing that's asked of us, and we get the tension. Once we get the tension, we can solve for the other things in these 2 equations. Okay, Tx is actually equal to Hx. We can solve Tx by looking at the component of T, and we get that value for the horizontal component of the hinge. And then we get the vertical component of the hinge by plugging into this top equation there.